we're going to talk about how very, very basic circuits work. Just getting your electrons to get them to flow. And we'll talk about what happens when you hook light bulbs up. And again, we are going to do this one virtually because it's easier when half the class is virtual, including me. Okay, so we are going to watch some videos to help us describe the lesson today. I'm going to describe it in my own words, but then we're going to watch the videos to help us understand, because just describing it is kind of hard to see. It's one of them that I'm going to rely on an animation to help get the point across. So today what we're going to talk about is current and very basic circuits. So current is the number of electrons that pass through a point in 1 second. What we were measuring last time was voltage. Which I want you to notice I'm putting energy in quotations. It turns out voltage itself is not actually an energy. We're going to describe it in the same ways that we described our other potential energies, but voltage itself actually is not an energy, but it's a potential to create energy. It's a nuance that you're not even going to need to worry about in this class, just letting you know it's not actually an energy. So what happened is, in your penny battery, we had metal 1 and we had metal 2, and we had them in an acid solution. This will actually also work in like tap water, because tap water has minerals in it. Distilled water it won't work so well in. But anything that has some minerals in it that makes a good conductor to get those electrons to move, it works better in vinegar and salt and making more of making your acid stronger. But what's happening, let's use a different color here, is, let's even just go like that. Our electrons are getting stripped away from one metal and they're going to the other metal. Atom by atom. Ah, I thought I saw Conrad in the background. I see him now on Ivan's screen. There we go. How many of you had chemistry before this? A couple of you. Did Mr. Miller talk about how, while it's important for atoms to have a neutral charge, that is their goal, it also is a natural goal of atoms to fill their electron cloud? Did that come up in chemistry, filling the electron cloud? Maybe it did, maybe it didn't, I don't know. It's one of those topics I wouldn't necessarily fully expect, but also wouldn't be surprised if you would have covered. This is getting into the chemistry of it all. But we talked about how there's the nucleus. And then around the nucleus, there are what we call electron clouds. And each electron cloud can hold a very specific number of electrons. So, level 1 can hold up to 2 electrons. Level 2 can hold up to 8 electrons. Level 3 can hold up to 18 electrons. And conveniently, mathematically, the number, or the maximum number of electrons that can be held on a cloud level equals 2n squared, where n is your level. That's something that you do not need to know from my class, but when you take a chemistry class next, whether it's at Ames or in college, something helpful for that class. So what happens is our electron clouds want to be full, and so I said you can hold up to, but you can also hold less than. And so what's going to happen is your metals are naturally going to take away the electrons from the clouds that were not very full at all and try to give them to the clouds that are almost full. So what happens here is when you put a battery in a circuit, and a circuit is something as simple as you add wires and you close it off. So here's my battery. We have our plus side and our minus side. And I'm just going to connect it with wires for now, but we'll show you in a little while why that's a bad idea. Your electrons are naturally in the battery, getting pushed through the battery. But what happens when it's hooked up to a circuit is we do start to have some instances where the electrons start pushing each other, and those electrons actually will continue pushing around the wire. Sorry. Peyton wants to teach too. And what happens is the push here pushes the electrons everywhere. Which creates a flow of electrons. Hey. Okay. I just was pulling this up and then apparently I didn't save it. I do have 2 videos, like I said, we're going to watch. We're going to watch them for their animation. I have put them into your lesson 36.1 page, so you can pull them up anytime you'd like as well. Let me go ahead and make sure I'm sharing sound. If you haven't copied down anything in the notes, go ahead and get it copied down. Oops. Okay. I can see Gabe looks like he's getting on a phone. Everybody else looks like they're looking up. Conrad's wandering around the room. Okay. Let's go ahead and get going with the video. It took me quite some time to find a good explanation of how these electrons move and why they move. And this is probably my favorite. Most of them just get into the straight into the math, but I wanted to spend some time on this concept first. Let me make sure one more time I shared the sound. Okay. All right.
The simplest electric circuit is a light bulb and a battery. The battery creates a force pushing the charged particles in the wire.
Okay, now I'm already pausing it. The battery does not physically lift the other side of the wire. I think that you guys would be aware of that. But they're going to use our ideas about gravity to reinforce what's happening through the electrons. And she's going to describe this, but the battery is basically like not as just an elevator, but it's a push. The battery pushes the electrons to this higher level. And what's going to happen is our electrons just naturally, on their own, want to fall here at the light bulb. And so we're going to see what we call a potential drop across a light bulb. And this happens with all light bulbs. Pause for you to copy that down. Alright, and Gabe, the fact you wear glasses and you're in a dark room gives away the fact every time, or gives away every time you're on a light changing something. Physics in play. And again, potential is not an energy, but it behaves very much like the energies we're used to. Okay. Can I clear what's on the screen? Okay.
Causing them to flow in a loop around the circuit. The number of charged particles that pass by each second is what we refer to as the current. The charged particles flow through the light bulb because the battery causes them to have a higher potential energy on one side of the light bulb than the other. This is similar to how objects at higher elevations have a higher gravitational potential energy. This potential energy is what we refer to as voltage.
Okay, and if I remember correctly, I don't think she gets into it, but if you have a stronger battery, a higher voltage, that means it also is going to have a higher voltage drop for the light bulb. Actually, she might get into part of this, but I'm still going to go ahead and write this down. But the greater the voltage of the battery, the greater the potential drop across the light bulb. And when you have a greater potential drop, the light bulb gets brighter.
If we visualize the potential energy as boxes that are attached to the charged particles, then we will see that this energy is converted into light as the particles pass through the bulb.
So it's a different way of saying what I had said before, but here they're talking about that potential is giving the electrons energy.
The charged particles regain their potential energy as they move through the battery, which pushes the charged particles to the higher potential.
Those blocks with E are supposed to represent the energy given to the blocks, or energy given to the electrons.
When the energy inside the battery is depleted, the battery will no longer be able to create this potential energy, which we call voltage. A battery that has not yet been depleted ensures that the voltage between its two terminals is always at a specific value.
Oops, didn't mean to go back. So when the energy is depleted, that means that those electron clouds have reached their equilibrium. They are no longer trying to strip the electrons from one side to take them to the other. Those clouds have been filled. So the batteries that we created in class, they would be depleted very, very fast. Your penny batteries just naturally will deplete very, very fast. Whereas the batteries that you put into your devices, or the batteries in your cell phone, or whatever you're using that has battery power, those battery powers have been, especially if I remember correctly, I think the acid has been created in such a way that it will be more controlled about how it takes the electrons. So it's going to, I wouldn't necessarily say it's a slower trickle across, but it will not deplete on its own naturally as well. Which is why your batteries, if you don't have them in a circuit, they will deplete, but it can take years and years and years for your standard AA to deplete itself. But if you leave it in a device that's running, you can actually deplete your batteries much more quickly because those electron flows are causing the electrons to strip from one metal inside the battery, put it on another metal, and once those clouds have reached their equilibrium, they no longer want to move the electrons, so they won't force it through the circuit either.
If we place several batteries with the same voltage together in parallel, then this will result in more energy that is stored, and this will give us more time before the battery is depleted.
We'll come back and talk about this, but not yet. Nilisha, you still with me? Ahmed, you still with me?
If we instead place these batteries in series, this will cause their voltages to add, resulting in a much higher potential energy for each charged particle.
Tanner, you with me?
A higher voltage across the light bulb means that a higher current will pass through it.
So, have you ever bought light bulbs for your home or for your own purposes? Have you ever noticed that they rate them in voltage? You can buy a 12 volt light bulb. You can buy a 60 volt, or actually it's more watt on that case, but the voltage across them is related. And what they're saying here is when it's a higher voltage, it means naturally it's going to increase how fast these electrons will pass through it. And when you have a higher voltage on your number on the light bulb, you're going to get more electrons passing through it in a second, and more electrons in a second will give you a brighter bulb. So your lower voltage bulbs will be pretty dim, but as you go higher and higher, they'll get brighter and brighter.
This will cause far more light to be emitted by the light bulb, but it will also mean that the energy in the batteries will be depleted much faster.
That's the end of that one, pretty much. Now, they brought up a concept that they use this on their batteries. But we're going to use it for mostly in talking about other circuits. They brought up the idea of parallel versus series. And that's going to be a big topic for today and for Thursday, or Wednesday for your class. Which, if you've been paying attention to the calendar, you know we're almost done with the school year. Wednesday will be your last lesson of the whole year. And then next week we're going to do your test. So parallel and series are going to come up both today's lesson and Wednesday's lesson. Have any of you had Hendrix electronics class? Anybody here? Okay. Have any of you ever learned about the idea of parallel versus series in a circuit? It's one of those I don't necessarily expect that you would have, but some of you maybe, depending on what your experience is. Tanner's either nodding his head or he's singing bop in his head.
I'd say I think so.
You think so? Okay, it's something that is fundamental to all circuits. And it's not just batteries you can place in parallel or series. Today we're going to focus on light bulbs in parallel or series. And then next class we're going to focus on resistors in parallel or series and explain that next time. But what they did was they had their battery. So if you're in parallel, we have our batteries. And they literally are parallel to one another. And remember, this end with the little nib at the top is your positive side, and the end without is your negative side. What happens with batteries that are in parallel is their positives are connected to each other. Sorry about Peyton. And their negatives are connected to each other. And then here we're going to have a light bulb. And connect to that as well. I don't think he'll be happy too long down on his plate mat, but we'll see how long that lasts. When you're in series, your positive is connected to the negative of the next battery. And again, I'm going to put a light bulb in here. I guess that's one way to take notes, Delisha. The days of technology. Even in the classroom, a lot of people that say, "Can I take a screenshot?" And I'm like, "Yeah, go ahead." Or not a screenshot, but take a picture. All right, so when we talk about the batteries versus the light bulbs versus the resistors, obviously there's some different things in play because those are different components. But what they said was, with batteries, connected in parallel give same energy as one battery, but they give that energy for a longer time. Whereas with series, in series, and so it just depends on what your goal is with your circuit as to which way you would organize your batteries. If you've ever had any device that takes more than one battery, if you just were able to pull apart where those batteries are going and look and see how the metal's connected, you can see for yourself if it's in parallel or if it's in series. Is it trying to connect the positive to the positive or the positive to the negative? And sometimes it's hard to see. In fact, most times it is, because most times that's encased in the rest of your device. But it's just going to be 100% based on what the goal of the circuit is. Well, I would say roughly half of your circuits that you deal with, battery-powered devices, are in parallel, and roughly half maybe are in series. Actually, I would probably guess a few more in parallel, because usually it's the longevity you're going for. But that's far to say it's definitely not all of your devices. Okay, so I have another video that we're going to watch, and it's going to talk a lot more about the light bulbs. And then after this next video, we're going to put you on an interactive where you're going to practice with these things.
Same charge repel one another, and they therefore spread out.
Oh, sorry, that started early.
Suppose we take our circuit of a battery and a light bulb, and we make it slightly more complicated by adding a switch.
Have you ever encountered a switch in a circuit? When have you encountered a switch in a circuit?
Legit turning on or off any light.
Legit. All right, so your switch is any on, off, switch, button, etc. So literally your light switch, what it does is it's breaking the circuit. It breaks it so the two pieces of metal can't touch each other. That's what a switch does, is it physically breaks the circuit. And what this is getting at, and this is going to be a huge concept for circuits, is electrons can only flow in what we call a closed circuit. Closed circuit means the switch connects the wires. Once that circuit is discontinued, once we have any break, your electrons will stop flowing. And so again, your light circuits, any button that you press, it's physically pulling apart the wires so that they can't touch, so we don't have this happening. Is Conrad still around there? Oh, there he goes.
He's not feeling well, so he's dipping.
Okay. Yeah, hopefully he starts feeling better then. Okay. Tanner, did you finish copying this down?
Yes.
Okay.
When the switch opens, the charged particles are prevented from passing through. Particles with the same charge repel one another, and they therefore spread out throughout the wire. The events shown here all happen at the same time, and this is the result. For the light bulb to turn on, the switch must close so as to create a complete path for the charged particles to flow around the loop. If we have several light bulbs, each light bulb can have its own individual switch.
So realistically, in your house, this is kind of what very, very basic idea of what your wires look like behind the house or behind your walls. I know, like this house that we're in, you saw first quarter I was downstairs in a room that had no ceiling. We're remodeling our house little bit by little bit. So I am not a skilled electrician, by the least. I understand the fundamentals, but not brave enough to actually go tinker with it, because electricity is something you want to be super careful about. But realistically, multiple rooms will be on the same circuit, and you can turn off the light switch in one room and it won't affect what's happening in the other room. This is what's happening. So like right now, the house I'm in, sorry, I'm gonna have to get him again. The house I'm in, the whole upstairs is on one circuit. So when I turn on the light in the bathroom, it doesn't affect the light in the kitchen at all. But I'm turning off and on individual switches and the electricity is still flowing.
Or we can have one switch which controls all the light bulbs.
Which I'd be turning off the electricity to the whole house, like at the circuit breaker. Or the whole circuit, I should say.
The number of charged particles that pass by each second is what we refer to as the current. The charged particles flow through the light bulb because the battery causes them to have a higher potential energy on one side of the light bulb than the other. This potential energy is what we refer to as voltage.
Okay, there is some information that's in both videos, so that's a repeat of what we've already copied down.
If both sides of a light bulb are at the same voltage, then no current will pass through it. As the voltage across the light bulb increases, the amount of current through the light bulb also increases, and the light bulb produces more light. When a switch closes, it causes the two different parts of a circuit that it connects to be at the same potential energy.
So watch what's happening here on this one. They have their circuit, or their switch in kind of a tricky place. So they have their electrons are dropping on each of these kind of stair-looking things. But when they close this circuit, watch and see what happens. What happened to that middle light bulb?
Turned off.
It turned off. We have a circuit here where all 3 light bulbs were on, but because of the placement of where they put the switch, it caused the electrons to have the same potential, so they don't have any motivation to drop there. They've got another path, and they just bypass the light bulb completely in this case. Let's see. I remember, yeah, right around here I want to go through. So that a little bit.
All points that are directly connected to each other through metal conductors and closed switches are at the same voltage.
So in parallel here,
This means that if we have
have the
several
same
light bulbs
voltage.
connected to a battery in parallel,
I'll write
the
notes on that.
voltage across each light bulb is equal to the voltage that is produced by the battery. Since the voltage across the light bulb determines how much current passes through it, each of these light bulbs will have the same current pass through it as we had when we had just one light bulb connected to the battery. The total current drawn from the battery is the sum of all the currents drawn by each of the light bulbs.
okay, let's go ahead and take some notes on that, and then we'll come back to what happens in series. So I am just going to sum up what they said. And again, the animation, I think, really helps to make it a little more clear what's happening here. When we have light bulbs in parallel, the voltage across each light bulb is equal to the voltage of the battery. So for example, if we had a 9-volt battery here, we would see a potential drop of 9 across each of these. But the current is not constant across each piece. Let's introduce a new variable for you. I is going to be the letter we use when we talk about our current. The unit of current is called an ampere. And so we get this summation here where before our V of our battery, which I'm going to call the V total, equals V1 equals V2 equals V3. And these things will not behave the same once I put those light bulbs in series. The properties are going to be completely different once I just change how these light bulbs are put together.
Now, let us consider a situation where we have several light bulbs connected in series. Since the total voltage across the group of light bulbs is at the specific value set by the battery, the drop in voltage across each light bulb is only a fraction of this.
Now you can't really see it here when compared with the previous light bulbs, but can you see the general brightness of those bulbs here down at the bottom? What do these look like in comparison? Are they brighter, dimmer, or the same?
They would appear to be dimmer.
They appear to be dimmer, and they will in fact, if they are the same strength light bulbs, they will in fact be dimmer. So, sorry, I'm trying to take care of him and take care of you at the same time. So, light bulbs in series are dimmer and because they're in series, the electrons will pass through them at the same rate. I'm going to take this back to the notes page and we'll just finish with the video here. So one thing I should add up here with our parallel situation, light bulbs in parallel will remain just as bright as if there was only one bulb. What happens here is there's going to be a voltage at each of our batteries, or each of our bulbs, and our total voltage through the battery will be the same thing as our combination of volts. But from the animation, we can see when they're in series, those electrons have to travel at the same speed because they're part of the same. We often don't think of it as like a water hose. If you're on the same water hose, it should make sense that the electrons at the front of the hose are going the same speed as the electrons at the back of the hose, or water in that case. So what happens here is when we talk about our current, oops. Here your current remains constant, but your voltage will change. And the result is, because we have this relationship with voltage, the light bulbs get dimmer as you add more bulbs. Okay, when you're ready, head to assignment 36.1a. This is the interactive that we're going to do today. We're going to use this interactive both today and next class. And you can create your own circuits. Very, very basic, but you can create your own circuits. So we have a battery here, and the battery we will adjust the voltage. Right now I can see this is a 9-volt battery because it's got the 9 on that plus side. We're going from 0 to 9 voltage. And you have wires that you can place. By the way, I mentioned you always do want to have an electronic component in a wire. If you do not, your electrons will pass through the wire too quickly. And when things move really, really quickly, there's a lot of friction, right? And when there's a lot of friction, what happens? Rub your hands together really, really fast and tell me what you feel. Go on, do it. Rub your hands together. I've got a sleeping baby falling asleep. What do you feel in your hand?
Heat.
Heat. What happens here is, this is just kind of a note for you if you ever build your own circuits. If there are no components to slow and control the flow of electrons, we have what's called a short in the circuit, which can be dangerous because it produces heat, and a lot of heat. Like, you can start fires with heat. I know about 4 or 5 years ago, I would say, I was teaching this unit, and I had, you guys that were in the classroom, you used the alligator clips, that I had those on the LEDs. I was making a really, really basic circuit, and I had those alligator clips, but I had the wires for 2 different things crossed, and that plastic wasn't enough to keep the electrons from flowing. I shorted out my own circuit, or I can't remember if it was me or if it was one of my students, but I do remember it was one of the students was like, Mrs. Miss Whitbeck, my circuit is smoking. And we look down and the plastic from the 2 alligator clips had melted together. And Hendrik still has that in his room held up. He's got mine plus a couple examples of students where they've accidentally melted their wires together. Because your electrons are bypassing all your circuits. And you can see here, your battery is flashing red to warn you that there's heat, where in real life they will not flash at you. So what we want to do is we want to put in a component. And today's component is we're going to use a light bulb. And just something as simple as a light bulb will slow the flow. I no longer have a battery that's blinking red. And I can see that I have, well, it's hard to see, a potential drop. Sometimes this is referred to as a delta V. Sometimes it's just referred to as a V. Maybe V1 if there's more than one light bulb. Okay, so a couple other things. You also can take out a wire and put in what's called an ammeter. Which measures the current. So ammeters are found on that multimeter that I gave you. It's a voltmeter and an ammeter, and it'll measure your resistance, which again, resistance is what we're going to cover next class. And so I can see here, let me use a different color so that pops a little bit more. I can see here that I have a current equal to 0.9 amperes. My total voltage is always the voltage of the battery, which would be 9 volts, which I don't think I made a big deal out of that, but V here is volts or voltage. And again, volt was the last name of somebody who studied the subject. And I can see my potential drop over here was also 9 volts. Okay, so for our interactive, you're going to be putting your light bulbs in series and in parallel. One more thing I need to show you is you can adjust the voltage of the battery or the resistance of the light bulb. So if I come over here to the slider, and then I've got this magnifying glass. If I click on the component I want to change, I can change the voltage to whatever I need it to be for my interactive. You also can take it to a light bulb and change the resistance of the light bulb and see what happens to, that was kind of hard to see potentially, but there is a perimeter here for the brightness. And as I change my resistance, you can see how that brightness changes. There it got dimmer because that circle is smaller. Here, when I have less resistance, it gets brighter. Okay. So, I know you might not have colored markers at home, but somehow for this first one, when it asks you to color code your potentials, somehow just label this is the highest potential, this is the lowest potential as you go. We're going to create a circuit. They want a 9-volt battery, they want a light bulb, and then they want an ammeter. And then a light bulb, then an ammeter, then a light bulb, then an ammeter. And so you'll go through and you'll create this circuit. And you'll label the pieces that are inside. Oh, and then let's see, I do need to change my voltage of my battery back to 9. Okay. Do you have any questions? Okay, I think I've shown you all the pieces you need for this circuit builder. And I'm going to let you guys go through. I'm going to throw you into breakout rooms so that you can have somebody to talk to. I'll just do one breakout room for the people in the room and one for the people who are at home. And I want you to go through, it shouldn't take you long to go through today's interactive. You're just doing one in series, one in parallel, and observing what's happening. And then all we'll have left after this is the homework, which we might even get to before class ends.